Hey guys, and welcome back to those of you who did not get lost in your YouTube feed, scrolling through all those videos and stuff. We're back for our final section. This is the last video. We're going to try and keep it as short as possible. Good news is 5.6, a lot like 5.5, is just an application of the previous section. We're just going to be using the previous section to determine some new stuff. So really the only thing we really need to know is stuff from the previous section. So we're going to be using a lot box method, which is the same as the double distributive property. Now, I personally, I think the box method is the most enlightening. So it's going to be the one that I use to show all the examples. But guys, if you like double distributive property or distribute, or even if you guys liked FOIL from high school, those are all fine. Perfectly good ways to multiply. The one limitation, I will say, of the double distributive property and the distributive property and FOIL, these guys all together, they have one weakness, and that is that they only work for binomials. Most of the time, they only work for binomials. So the box method is good because it works for trinomials, binomials, quadnomial things, whatever. Now, of course, in our class, we don't want to waste you guys' time, so we're only going to be doing trinomials, trinomials, and binomials is what we're going to see. So a lot of us, we're going to use the box method for that reason. Okay, so there's just we have some drawings. You guys remember from last time, we're going to have like our terms grouped together, and then we're going to try and find the area of this box by breaking it into sections: x times x, 3 times x, x times 7, and then 3 times 7. And then we would just add up all these pieces we get over here to some new algebraic jargon that we would then simplify. So usually we're going to get some like terms that are diagonal from one another in the box method, another nice quality of it. And we'll see it in action here in a second. So the purpose really of this section is we're talking about special products and squares. And you might remember, they look something like this. You guys may remember from previous sections. We've seen stuff like this before plenty of times. Talked about it a lot. There's a few test questions that have been some examples kind of hinting at what we're going to do in this section. And for us, really what we want to talk about are these special products, because in the next chapter, we're going to talk about factoring. And if you guys, let me just tell you, if you cannot figure out these guys, factoring is going to be really, really tough. So don't worry, all it is just more box method, more FOIL, whatever. Okay. So I want to say we're looking at this guy right now like we would a formula or an equation, any equation for that matter. These terms here, A and B, could be anything. They could be absolutely anything. You could plug in whatever you want. You could plug in a number, 3 and 4. You could plug in a number and you could get an answer. You could plug something in and get an answer, whatever you wanted to do. You could plug in the same number. You could plug in 3 and 3 if you wanted to, right? A and B are anything. But when I say that, I mean literally anything. You could also plug in for A 3x squared. That could be something you plug in for A, for example. Like you could put 3x squared in here, and that still works. Like that's still a viable choice for A. And likewise for B, you could pick something even crazier, 336y cubed. Something insane could also go in there for B, right? You can plug in anything you want, any term you want. It doesn't have to be numbers. So just keep that in mind as we go forward. We're looking at something. Really, what we mean by A plus B here is we're looking at all algebraic structures that have the form something plus something in parentheses squared. That's what we're talking about in general, and that's what makes algebra so cool. It's because we can talk about anything we want in general. So I'm just gonna think about this guy. I want to find a reduced form board. I really want to multiply. Maybe the instructions should say multiply, because I really want to multiply these guys out. So that's what I'm going to do. Well, A plus B, that's the same as A plus B whole squared. That's the same as A plus B times A plus B, right? That's the same as A plus B times A plus B. Well, that's what we just did in the last section. We just looked at what we could do here. We could double distribute. We could pick these guys up and box method them, which is what we're going to do. We could use FOIL first, outside. Whoa. We could do the first, outside, inside, last is the FOIL thing. You guys can do that if you want. I'm not a big FOIL fan. For us, we're going to use box method. So I'm going to come over here, draw my box. Guys, look at how steady my hands are. Come on. Ooh, there I go and ruin it. Oh, actually, let's come over here and draw a box. I think I can do this. Nice. Oh yeah, pretty cool. Pretty sweet. So here I'm going to have an A plus B. Now I'm not going to, yeah, let's do different colors. Here's an A and a B, the blue guys. So this will be blue team right here, and then over here could be, I think this is, yeah, green team, A and B. So, guys, don't forget, don't lose your minds just because we're looking at new variables, right? This is still just something times something. This is still a monomial. It acts exactly like a monomial. We have a degree, I should say, excuse me, a variable a and variable a that are both degree 1, with a little 1 hanging out up there. So we can still multiply them, just whatever. They have a coefficient of 1, a degree of 1, but they act exactly like monomials. So that's what we're going to do. Well, a times a, that's just a squared. Ooh, I'll do white here, maybe. A times a, that's just a squared. A times b, that's just ab. And then same thing here, that's another a times b. Right, so just a times a, that's a squared, right? Here's a times a. And then here's a times b, just ab. And then same thing going on here. And then here, just like for a, we saw b, so there's two b's. Excuse me, I should say b times b, which is b squared. And then over here in my output, I'm just going to have a squared plus, and then here, you'll notice, actually in this case, and guys, I will say, this always happens in this form. If you have this form, then yes, the diagonals are always like terms. We actually have an AB and an AB. Now I'm gonna write it like this. I'm gonna write them both out first, but you could, if you see the simplification, then go ahead and do it. We're gonna say equals. Oh, and my equal sign here. This is this equation. This guy's equal. And then we'll say a squared here. And then guys, I have two. My variable part for these guys is AB. They both have the same degree. So we're good. We can add those, and there's actually two of them. So we're going to say this is 2ab plus b squared. That's really all for this example. These come up all the time. This is called the square, the binomial, I should say, the binomial square. Comes up all the time. This is just an expansion of the binomial square. You actually might even call it the binomial square expansion, honestly. The binomial square expansion. I encourage you guys at home to try and up this number to 3. See what happens. See something crazy happens. But we don't have time for that. We're not going to do that today. We're going to move to the next one. It's very, very similar. Very, very similar. Here has an a minus b. Guys, isn't this the same as a minus b, a minus b? That means we can box method this just like we did last time. Okay, well, let me draw a box. Oop. And then we'll separate this section. I want a little more space for my A. A and B, nice, and then there's this. A and B. And then, oh, I should say this is negative B, right guys? This is negative B. Because we're going to be plugging in. This term is no longer B, it is negative B. Guys, can I just say, negative B is not B. They're very different. Very, very, very different. So remember, those negative signs are super important. In fact, they're opposites. They're exact opposites. So here in this case, we'll say a times a, that's a squared, like we saw last time. Now, negative b times a, well, you can think of this. Remember, guys, we can think of this like there's a negative 1 and a 1 here for these coefficients. So really, we're thinking negative 1 times 1. Well, that's negative 1. And then a times b, right? That's got to be ab. So we have a negative 1 times AB, which is the same, I'm just going to write it like this, which is the same as minus AB. And then isn't this square the exact same? It's a minus B and an A. So it must be the exact same thing. It's going to also be minus AB. And then here, guys, we have a negative B. So there's a negative 1 here and a negative 1 here. Well, negative 1 times negative 1, that's a positive 1. And then we'll have a b squared, right? So same thing here. We'll actually get a plus b squared. Of course, dragging my terms out, dragging my terms back out, we'll get minus 2, minus 2ab, because there's two negative ones, plus b squared. Very, very similar to the last one. Very, very, very similar to the last one, except one key difference. There's a minus on this second term. So whenever you have a minus inside these parentheses, the result is you're going to have a minus here. And now, guys, if you ever run into a problem like this, you could always do box method again. You always could. The problem is that we want to be able to quickly recognize whenever this happens, whenever these forms happen, so that we can factor things later. So, although it seems like this is redundant because we've already learned box method, I'm encouraging you, please try and remember these. They're very important, not only for this class, but later. There's tons of factoring in your next classes, so please be aware of that as you move forward. So just a quick refresh. When you have a plus, we have a plus. Okay? Over here, when we have a negative, you have a negative. So not too bad. They're pretty similar. We do the kind of the same thing we've been having, right? So we're going to look at one more case, and then we're going to look at an example, and that'll be it for sections 5.5 and 5.6. Here's our last example. This guy is very, very special. Actually, I didn't even write anything on the slide because I wanted to talk about him so much. This guy's so cool. Comes up in factoring all the time. It's like used often as like a trick question or maybe a throwaway to try and get people to mess up or trip up. But I don't like it like that. I think this guy's awesome because he demonstrates something in math that we use all the time. So you'll notice the key difference here is that we have an a plus b and then an a minus b. Now there's no way to write this like, you can't write this like a plus b squared. You know, you can't write this like, excuse me, my iPad's crying. A minus b squared. You couldn't do that because we have a plus here and a minus here. We might say these b's, they're opposites of one another. They're opposites of one another. So we don't have a square. In fact, what we often call this guy is the difference. Since we have a b and negative b, we call this the difference of squares. This comes up all the time, and we will see. We will see why it is called the difference of squares here in a second. This is maybe not such an enlightening form, but we'll see why it's called the difference of squares whenever we do our FOIL. We'll also see why it's so useful in all kinds of mathematics in just a moment, because of its super helpful factored form. Anyways, so here I'm going to translate what I got. My first one, maybe we'll do it in blue. I have an A and I have a minus B. Excuse me. I'm so sorry, guys. A and a plus B. That's from this guy. So there's blue. I don't know if those are the same blues or not, but I think they are. And then over here in green, I think that's also blue. This one maybe over here in green, we have a minus b. So I have an a and then I have a negative b, which makes it distinctly different from the first term we just did. So we're going to go ahead and multiply these just like we've been doing using our box method. So a times a, that's still a squared. Nothing changes. Very nice. Now b times a, we know that's a times b. They're the same, right? We usually write the, like, alphabetically. We write our alphabetic first. So a times b. You could write b times a. That's the same. And then here we get a negative ab. Just remembering that there's a negative 1 here and there's a 1 here. So negative 1 times 1 is negative 1 ab. And then here we have a b plus, or excuse me, a plus b times a negative b. So same rules apply. We have a negative and plus. So we're going to get a negative, and then we have b times b, which is b squared. Now something crazy happens whenever we write this guy in its expanded form. Whenever we write this guy all multiplied out like we just found. So all I did is translate what we knew, and this guy is equal. It looks like I'm saying, sorry guys, it looks like I'm saying the box is equal, but that's not what I'm saying. I'm saying this guy is equal. So expanded out, it looks like this. And now look what happens here, guys. Here, we have a plus AB, and here we have a minus AB. So these guys cancel, right? Or I shouldn't say maybe they don't cancel, but they equal 0 when you add them. So you get 0 if you add these guys, so we won't even write them. AB minus AB, that's nothing. And so we'll just be left with my, we'll write to 0. And we're left with a squared minus b squared. So this guy, look at this. Look how cool this is. This guy's factored form, which we'll later see more about in the next chapter, looks like this. A plus b, a minus b. This comes up a ton. Now we're going to use these right now as a shortcut, and in the homework that's kind of what they want you to do is plug in some stuff, use it as a shortcut. So what we're going to do is use these guys as shortcuts. So this guy, our first example here, to me this looks like something squared. So I'm going to call the first thing A. That's way too thick. The first thing A. And I'm going to call the second thing B. And there's a minus between them. So I know from the previous slide, this should be a squared minus 2ab plus b squared. Okay? So I've called xa, maybe we'll underline them in blue or something. And we called this negative, or we called 1/2 b, and we're leaving the minus sign out. So we had to call 1/2 b. And I'm just going to plug in what I know. I'm just going to go through and plug in what I know, guys. So here I've got an x squared minus 2 times a, which is x right now, times b, which is 1/2, plus, and then I have a, I meant to do that in white, plus, and then I have a b squared, which is 1/2, and now I'm going to use my parentheses, because I'm plugging it in. And here we get something very cool. Equals to, well, x squared, that's just x squared, right? And then half of negative 2x, that's just negative x. Half of 2 is 1. And then here, of course, 1/2 of 1/2 is 1/4. You can also think of this like distributing on, and distribute's a strong word. It's this exponent rule. These guys are both squared, so 1 squared is 1, and then here 2 squared is 4. So we get 1/4. And not too bad. And look, you're done immediately. Look how fast that was. And later we'll see this guy's factored form, the factored form of this expanded form, so we often call this the expanded form. This guy's expanded form, and here's his factored form up here. So let's try with this example, and then we'll be done. So this guy does not look like something squared to me. It looks like I have something, an a minus a b, and then I have that same a plus a b. Now guys, if these had been different numbers, like, let me just erase real quick. Let me just erase real quick, just for example. If this had been 3, this is totally different, because now I have an a and an a, but I can't call this b and then call this b, because then I'll be calling b two different things, a 3 and a 6 in this case. So just keep that in mind as you're checking around for these. We're going to require these guys to be the same, so we can call them both b. Alright, and then right here, we know this to me looks like a minus b, a plus b, which is the same as a plus b, a minus b, right? So this is equal to, we know this should be equal to a squared minus b squared. So I'm just going to plug in what I had for a. In this case, it's p squared. Here's my p I'm stealing for a. And then my 6 is playing the role of b, so I have a minus. And then I'm going to plug in 6, all squared. Well, p squared is just p squared, right? No way to simplify that guy. But 6 squared, that's 36. And guys, you're done. Since these two guys have disagreeing variable parts, one guy's a p, one guy has no p's, p to the 0. That's done. You're simplified. So there's an example of using it to quickly multiply. I know it seems like kind of redundant. Yes, you could have just used FOIL or box method or whatever you wanted to use. On these guys, it would give you the same answer. I encourage you to try it, see if you get the same answer, see if it really works like it should. And by the way, it definitely does, because we've just proven it time and time again. We've proven it, these relationships, using the box method. But I encourage you, test them out, try them on your own, see what goes on, see if you find some shenanigans going on, and apply these methods on the homework. Most of the homework is testing your ability to use and plug in A and B effectively. Guys, without further ado, I'll see you on Tuesday, where we'll pick back up this discussion and we'll start doing what we just did in reverse. It's called factoring, and it is so useful. So make sure you're there for that.